Hello, and welcome to our video on radical reactions alkane halogenation. This is part of organic chemistry. Usually this is the first radical reaction that you would learn, and so we're going to go over it in some detail. Now, hopefully you've already seen the introduction to radical reactions for organic chemistry that I made, so if you haven't done that, you might want to go back and check that out, so that way you'll be familiar with the terminology and sort of what we're drawing for the mechanisms, and then come back to this video so we can do the actual reaction. But for now, we're going to assume that you've done that, so let's go forward. So the reaction we're going to talk about here is called alkane halogenation. It's called this because we're starting with alkane, and then we're just adding a halogen. So you may have done this with, say, a double bond, but obviously a double bond adds a little bit differently. It should add 2 of the halogens. This one's only going to add 1. And here we're taking off hydrogen, so we're going to figure out how is that going to happen. All right? But before we get into the mechanism, let's talk a little bit about the special characteristics of this reaction. So the first thing that you might notice about this reaction, if we're looking at, say, example 1, is that it's regiospecific. That means that it makes one isomer product versus a different isomer product. So this is specific because we're putting the bromine on the middle carbon and not on one of the side carbons, right? So it has a choice and it's choosing the middle one for a reason, okay? Another thing that's cool about this reaction is it's the only reaction that we're going to have in organic 1 and 2 that has an alkane as the starting material. So alkanes are not reactive. We said that many times, that carbon-carbon bonds are really stable, carbon-hydrogen bonds are really stable. So it's really hard to get that off, say, like with a base. You'd be hard to deprotonate it. So because they're so stable, they tend not to be very reactive. So this is a special case where we can actually react an alkane. So that's actually pretty good. If you're doing a synthesis and you start with an alkane, you know you're going to use this reaction. The last thing we want to talk about before we go forward is that bromine and chlorine actually don't work exactly the same. So the bromine in this case is more selective than the chlorine. So we'll talk about why. But what that means, first of all, is that the bromine that we see product is going to be the only product. So that's the only thing you're going to get. The chlorine product is actually going to have this as the major product because it's more like stable in the process. But it's actually going to have a bunch of side products. So it's going to have all these minor products. So as you see, it can add a chlorine on the side, or it could add more than one chlorine. So once it adds one, there's not really a whole lot to stop it from reacting further because it's so reactive. So you can have multiple chlorine things. So what this means for us is that, generally speaking, if you're asked in, say, a multiple choice question, you might have more than one product for the chlorine. So look and see what the choices are. If there's more than one product, you might want to pick like all of these or whatever is the choice. For the bromine, it'll just be the one. Okay? What it also means is for synthesis questions, you don't want to use chlorine because it's not very picky. So you're not going to get the product you want in a very high amount. So you might get like 60% yield as opposed to 95% yield, for example, because you're getting a bunch of other stuff. All right? So we're only going to use the top reaction for synthesis. The bottom one's just going to be like, you should know it can possibly work. So now that we sort of run through what it has, let's talk about the whys. So why is this going to be more selective for bromine? And then we'll talk a little bit about why we're getting the regiochemistry that we're getting. So let's keep going. All right, so we're going to talk about 2 different things related to this reaction. The first thing we're going to talk about is halogen reactivity, and then we'll talk about the radical stability, okay? So when we're talking about the halogen reactivity, remember the halogens are the things that are in the same column as fluorine, right? That's the same group number. So these are the choices. And what we see is that fluorine would be the most reactive in this type of reaction, and the iodine would be the least reactive. So remember, we're talking about the initiation step. That's the step where the halogen is going to break into 2. So if I use X as the halogen here and I show the mechanism, remember it's going to be like an initiation step with 2 curved arrows, and they break apart to form the radicals, right? So the problem with these is that not all of these are actually practical. So when we look at fluorine, it's reactive, but it's so reactive that it's actually explosive and dangerous, so we would not want to use that one. So then we see that chlorine is on the more reactive side, bromine is on the less reactive side, and then iodine is so unreactive that it takes days to react. So obviously we're going to count that one off completely. So then between chlorine and bromine, why are we choosing bromine? Well, if you think about something being reactive, that means it's going to be less stable, and things that are less stable want to get to something that is more stable, so they're more likely to react with anything that's around them and not be picky about it. So that's why we said that it's going to add more than one chlorine sometimes, that it'll add in the wrong spot. So it's more reactive means less selective in this case. In bromine is the opposite. It's a little bit slower, but it's still going to react, and it's going to be more selective because it will only make the most stable intermediate, and that's going to make it only make one product as opposed to making any sort of intermediate, which then leads to lots of different products. So that hopefully makes sense. More reactive, less selective, okay? So that's why we're going to use bromine. That's why that's the best one. Okay. So now that we understand that we get some selectivity, let's talk about why we get the product that we do. So why that regiochemistry with the bromine, say, in the middle and not like on the end, all right? So we need to understand that radicals are electron deficient. They have electrons, obviously, because they have one electron, but they have an unpaired electron, which is less stable than paired electrons. So in that way, they are considered electron deficient, even though they don't have a charge or anything like that. So because they're electron deficient, we're going to consider them to be similar to a carbocation, right? That's something that we've seen before. So carbocation, what's the stability? Remember we said that the most stable thing was resonance. See, everyone forgets about resonance. So you probably said tertiary, right? A tertiary carbocation. And then secondary and then primary would be less, and then methyl would be the least. So we just do want to make sure we include the resonance on there. But yeah, so radicals are going to be the same way. So we start off with resonance. It would be usually stabilized. So we're going to put that here on the left for the most stable. And then methyl would be the least stable. So we'll draw a methyl radical. And then we'll have in the middle, filling them in, those will be the different radicals that you can have. So tertiary has 3 carbons on the carbon that has a radical, secondary has 2 carbons on the carbon that has a radical, and primary has 1 carbon on the carbon that has a radical. So that's sort of what they look like. Okay? So hopefully that makes sense, relating it to something we've already seen. But if you're confused about that, just, ask me questions, let me know. So now that we know all the theory about how the reaction works, let's see the actual mechanism. All right, so here's the example reaction that we saw before. So remember we said we're going from an alkane to something with a bromine on it, and that we're adding a bromine, but we're taking a hydrogen away. So we're going to have to make sure we account for that in our mechanism. Also, we're going to use the 3 different steps that we said in the mechanism of initiation, propagation, and that's all we're going to use. We're not going to use termination in our mechanism. So we're going to make sure we do that as well. Okay. So the very first thing we need to do for any radical mechanism is to show the initiation step. So in this case, we have light. That's going to be our initiator. So it's going to work directly on the bromine. We didn't have to add any peroxide or anything like that. So bromine, if exposed to the right wavelength of light, will split into 2 radicals. So let's show that. So we're going to draw the bromine over here. We need to draw out the bond. And then we're going to do an initiation step. So how many arrows do we need to split this? 2, right? We said 2 for initiation. So we're going to do 1 here and 1 here. Now, it doesn't matter to me if one's on top and one's on bottom, or if you wanted to draw it like this down in the corner. If you want to draw them both on the top, I don't care. As long as one's going to one side and one's going to the other side, that looks perfect to me, okay? All right, so then that's going to make a bromine radical. It's technically going to make 2, but we don't have to draw both of them because they're not going to do anything different. So we'll just draw 1 for now. So we'll draw that right here. So then once we have our first radical, now we can do a propagation step. So remember we said we need to lose the hydrogen and add the bromine. So obviously we can't add the bromine while the hydrogen's still there because carbon can't have more than 4 bonds. So the first thing we're going to do is take that hydrogen off. So what's going to take that hydrogen off is going to be the bromine. So we're going to use the bromine radical and we need to add that to the hydrogen. So we're going to do propagation. So how many arrows does that take? Right, it's going to take 3. Remember also we're using fishhook arrows, right? So we're going to take 1 off the spot where we're going to put the bromine. That's how we know which hydrogen to take off. So we're going to draw the bond first with the hydrogen. Then to break the bond, we need to take from the bond to the carbon. That's going to break part of it. And then the other part is we're going to take the bond and we're going to draw it just out into space for right now, right? Then the bromine's what's going to actually add to that hydrogen. That's what's going to make the bond. So we're going to draw an arrow from the bromine dot to meet up with where that hydrogen is going to go, right? And remember, we're just showing them a little bit further away so it's easier to see, but we know the bromine would technically be a little bit closer than this, okay? So then now we're going to draw the product of that step. So that's going to be a radical left over. So what's our radical left over going to look like? It's going to be the carbon with the dot in the middle, right? And then we're going to make HBr. That's a byproduct. You don't have to draw that, but if you want to, you can. That's just a byproduct, okay? So now, why did it make this radical and not take a different hydrogen? Because the other ones would be less stable, right? The other option would be this one here. And what kind of radical is that? That's a primary, right? And we said secondary is more stable than primary. So it's going to pick on anywhere in the molecule, where's the most stable radical going to be, and that's the hydrogen you're going to take off. Does that make sense? Hopefully? Okay, good. All right, so now we've got this radical. So now we need to get a bromine on this carbon radical. So how can we get a bromine? Where can the bromine come from? So in this case, there's a couple options, right? We have another bromine dot, we have HBr, and we have Br2. Now, we said we don't want to use termination in the organic mechanisms because the radicals don't tend to come together. They're not attracted to each other. So it's really hard for them to find each other. What we do have a whole bunch of is bromine because that's one of our reagents. In fact, we can add excess if we need to. So we're going to use the bromine reagent instead of using a dot, okay? So we're going to do a propagation step. So how many arrows do we need for propagation? 3, right? 3 curved arrows, fishhook arrows. So we're going to draw the bromine. It's going to break that bond as well. So we're going to draw that bond out. Then we're going to draw the arrow of adding that, right? So we're just going to go from the radical to space. Then from the bond, that's going to take one of the radicals from the bromine, and that's going to meet up to make a bond. Then to break the bond, we're going to draw an arrow on the other side to break that apart. Now, what's cool about this using propagation is that now we've made more bromine dot. And bromine dot was our first thing we had to make in the initiation. So instead of having every single bromine having to be broken apart by light, we actually only have a little bit, and then we can just make more as the reaction progresses. It makes more itself. So once the reaction gets going, it can go for quite a while on its own until basically we run out of one of the reactants, either the carbon substrate or the bromine. All right? So now let's go back and label the different steps that we did for what type they are. So what was our very first step? What type was that? Was it initiation, propagation, or termination? Right, it was initiation, right? We said the first step's always initiation, so that's right. Then what's the second step? What kind is that? Propagation, right? We can probably abbreviate, so propagation for that one. And then what's the last one? Propagation, right? Remember we said we don't want to use termination. So perfect. So it's nice to label them. The only thing that's actually required for me is the red part. So you just have to show the arrows, but it's nice to label them. It helps you keep track. All right, great. So hopefully this makes sense. If not, of course, ask me questions in class. Whatever you need, just let me know. All right, so we're almost done. Before we finish up, it's really important to make sure that you can predict what the product is of a certain reaction, right? So let's see if we can predict what the product of this reaction would be. So if it helps, you can try to think of what's the most stable intermediate. And the key step, remember, is removing the hydrogen to make that radical. So what would be the key radical we would have? Right, it's going to be here. And then that's going to make what product? Right, we're just going to put the bromine there. So perfect. So that's all you have to do. It's actually pretty easy. For box questions, you don't have to put the mechanism, right? You don't have to do the whole thing. But sometimes it does help to have the intermediate just so you can understand how it works. All right, great. All right, so with that, we are done with this video. You've now learned the basics of radical reactions and how to do a alkane halogenation radical mechanism. Hopefully it all makes sense, and hopefully this video has prepared you either to go to class or to do activities or whatever you need to do with this material. Hope you have a great day. Bye.